Welcome to Differential Equations, Lesson 2, a great method for solving first-order linear ordinary differential equations, integrating factors. We will look at a linear differential equation, first-order differential equation, like this, and we will see that multiplying an equation by an integrating factor can help us solve that equation. To motivate what we're going to be doing, let's start with a couple easy problems. The first problem, solve the derivative with respect to x of the function y of x equals cosine of x. If we look at this, we notice we can easily solve this by just anti-differentiating both sides of this equation. So in our solution, the integral of the derivative with respect to x of y of x dx equals the integral of cosine x dx. Now, here we have the antiderivative of the derivative of y of x. So that simplifies to y of x. On the other side of the equation, the integral of cosine of x dx is just minus sine x plus a constant. So these are solutions to that differential equation. We can pick any constant we want here, any value for this constant, and that would give us a solution to this differential equation. Now, let's make the problem just slightly harder. Let's solve this differential equation. The derivative with respect to x of e to the 2x times y of x equals cosine of x. This looks similar to what we had up here, except we have this extra factor of e to the 2x. Does that cause any problems? No, it doesn't. We can still anti-differentiate both sides of this equation. So we get the integral of the derivative with respect to x of e to the 2x y of x dx equals the integral of cosine of x dx. When we integrate the derivative of this function, we just get this function on the left-hand side, e to the 2x times y of x equals, and then the right-hand side, that integral, once again, is minus sine x plus an arbitrary constant. We can now algebraically solve for y of x by multiplying both sides of this equation by e to the minus 2x. Thus we get y of x equals e to the minus 2x times the quantity minus sine of x plus a constant. For any choice of a constant here, we would get a solution to this differential equation. Wouldn't it be nice if all linear differential equations of first order were this easy to solve? Well, the answer is they more or less are. What we're going to find is that we can, by using what's called an integrating factor, on this left-hand side, get something like the derivative with respect to x of mu of x times y of x equals some other stuff on this side, and then anti-differentiate both sides. So we need to come up with integrating factors so that the thing that we get on this left-hand side is the derivative of something so that we can easily integrate it. That's where we're headed. We are still looking at the equation derivative of y with respect to x plus p of x times y equals q of x. What we will see is if we define a function mu of x to be e to the integral of p of x dx, p of x being this function up here that's multiplied by y of x, this will be what we call an integrating factor. What we will do is multiply both sides of this differential equation by this integrating factor and then integrate both sides. Let's talk more about the integrating factor. We start with the equation, the differential equation, the derivative of y with respect to x plus p of x times y of x equals q of x. Multiply both sides of this equation by the integrating e to the integral p of x dx, and then we'll look at the resulting left-hand side of this differential equation. It turns out that e to the integral p of x dx times the left-hand side of this differential equation is equal to the derivative with respect to x of that integrating factor times y of x. Using the notation mu of x for that integrating factor, this equation can be written as the integrating factor mu of x times the left-hand side of this differential equation is equal to the derivative with respect to x of the product of the integrating factor mu of x times y of x. Near the end of this lecture, we will see why this is true. So the steps in solving our differential equation are going to be the following. We start with the differential equation. We use p to calculate the integrating factor mu of x. We then multiply both sides of the equation by mu of x. We then realize that the left-hand side can be written as the derivative with respect to x of y times mu of x. And the right-hand side remains as it was. Then we anti-differentiate both sides of this equation. If we anti-differentiate the left-hand side, we just get y times mu of x, because the integral of the derivative of a function is just that function itself. When we anti-differentiate the right-hand side with respect to x, we just have the integral mu of x q of x dx. Okay, then to solve for this function y of x, we use algebra. Divide both sides of this equation by mu of x, and that will give us a formula for the solution y of x. Example. Let's find all solutions to the derivative of y with respect to x plus 4xy equals 4x. So the first thing we do is we look at this linear equation, and the p of x function is 4x. So the integrating factor in this case is e to the integral p of x dx. That's e to the integral of 4x dx. This integral is just 2x squared. So we multiply both sides of this differential equation by e to the 2x squared. We then realize that this left-hand side is the derivative with respect to x of y times the integrating factor. On the other side, we just have the same thing as before. We now anti-differentiate both sides of this equation, and on the left we get y times e to the 2x squared, and on the right the integral 4x e to the 2x squared dx. Now, to evaluate this integral, we can make the substitution. U equals 2x squared, and du is 4x dx. That will make the integral of e to the u du. So the antiderivative of that is just e to the u, 2x squared. So we get from this equation y times e to the 2x squared is e to the 2x squared plus an arbitrary constant of integration. Now, solve for y algebraically by dividing both sides by e to the 2x squared. So we get y is e to the 2x squared plus c divided by e to the 2x squared. We can simplify this to be e to the 2x squared divided by e to the 2x squared, which is 1, plus c divided by e to the 2x squared, which is c e to the minus 2x squared. In that last problem, we anti-differentiated. In other words, we used the indefinite integral. Sometimes it's desirable instead to use the definite integral. This comes in handy especially if we cannot find a closed form expression for the integral of p of x dx. So we'll see that instead of using anti-differentiation, in this case, we will use definite integrals and the fundamental theorem of calculus. Our final answer, our solution, our general solution, will involve a definite integral. But in many cases, that is fine, because we can still graph that solution by using a graphing calculator or computer software such as MatLab, Maple, Sage, or Python. As an example, let's solve the initial value problem given here. The square root of 1 plus x cubed dy over dx plus 3x squared y equals sine of x. That's the differential equation. And we have the initial condition y of 1 equals 3. So the first thing we'll do is to get that differential equation up here in our standard form by dividing both sides of the equation by this square root. When we do that, we get the derivative of y with respect to x plus 3x squared y divided by the square root of 1 plus x cubed equals the sine of x divided by the square root of 1 plus x cubed. So far, we have this equation, and so now let's find the integrating factor. Think of this term as p of x times y, and so mu of x then is e to the integral of p of x dx. So we need to find the integral of 3x squared divided by the square root of 1 plus x cubed dx. If we let w equal 1 plus x cubed, which is right here, then dw is 3x squared dx. And so this integral becomes the integral of dw over w. We can easily see that that is equal to e to the 2 square root of w just by using our power rule for integration. And then substituting the fact that w is 1 plus x cubed gives us the integrating factor is e to the 2 square root of 1 plus x cubed. So then we will multiply both sides of this differential equation by this integrating factor. So we have the integrating factor times the left-hand side of the differential equation equals the integrating factor times the right-hand side of the differential equation. We now use the fact that this left-hand side is equal to the derivative with respect to x of the integrating factor times y. On the right side, we have whatever we have. So far, we got our differential equation in this form, and we would like to find the solution y of x. So what we'll do is use definite integration. First thing we'll do is just a change of parameter. We'll change this differential equation, which is an ODE for y of x, into an equivalent ordinary differential equation for y of t. Basically, we'll substitute t for the x. So this becomes the derivative with respect to t of y of t times e to the 2 square root of 1 plus t cubed equals e to the 2 square root of 1 plus t cubed sine of t over that square root of 1 plus t cubed. Now, we'll integrate both sides of this equation from, we're integrating with respect to t, integrate it from 1 to x. The integral from 1 to x of this stuff dt equals the integral from 1 to x of this stuff dt. So far, we have the integral from 1 to x, the derivative with respect to t of this function of t dt equals the integral from 1 to x of this function of t dt. Let's recall the fundamental theorem of integral calculus. One way it can be written is the integral from a to x, the derivative with respect to t of f of t dt equals f of x minus f of a. We'll use that on this left-hand side of this equation. We'll let f of t be y of t times e to the 2 square root of 1 plus t cubed. So if we do that on the left-hand side, what we would get, remembering that we are integrating from 1 to x, we'll get capital F of x minus capital F of 1. In this next line, here is capital F of x. It's the same as this function f of t with t replaced by x. Similarly, f of 1 is this, and then if we remember that fy of 1 is 3 by our initial condition, we can replace that with 3, and so we have y of x times this minus 3 times this exponential equals this integral. If we add this term to both sides of the equation and afterwards divide both sides of the equation by this exponential, we finally get y of x is e to the minus 2 square root of 1 plus x cubed times this factor. This gives us an exact solution to that initial value problem. Notice when I divided by e to the 2 square root of 1 plus x cubed, that was equivalent to multiplying by its multiplicative inverse, e to the minus 2 square root of 1 plus x cubed. Let's now consider a program, a MatLab program, to plot the solution function that we just found. The solution function looks fairly complicated. Y of x equals all of this stuff, and inside this formula we have an integral from 1 to x of this particular integrand dt. So we'll have to look at a program that will allow us to plot this sort of thing. We're going to use MatLab software to plot this. Octave software is open source and it is very similar to MatLab. The programming essentials are probably about 99% of the same on each of these platforms. So if you learn to program in MatLab, you can program in Octave or vice versa. The program that we will look at on the next slide uses programming concepts such as loops and arrays. If you are unfamiliar with these concepts in programming, you can look on the internet and find many guides to programming in MatLab and in other languages, and also quite a few video tutorials. So the idea of our program is, first of all, we want to plot this function, which is a solution to our initial value problem, and we want to print it, plot it for values of x in the interval from 1 to 4, for values of x greater than or equal to 1 and less than or equal to 4. So what we'll do is we'll take the interval 1 to 4 and we will partition it into 200 equal length intervals. The first endpoint of the first subinterval we'll call x1, and that's 1. Then we have x2, x3, x4, all the way through x sub 200 and x sub 201, which equals 4. This will give us exactly 200 subintervals. So let's look at a MatLab program to plot y of x. We'll start with a function which we call main, and the first thing this function will do is to clear the workspace. It will clear out any variables that already exist. Then we have a for loop that starts here with the keyword for, ends down here with this end statement. Inside this for loop, we're going to do something 201 times. We're going to define, first of all, x sub 1 of k, and the first value of k is 1, and then it'll be 2, 3, 4, 5, 6, all the way through 200. So when k is 1, we're executing all of these statements with the k value being 1. So the first x sub 1 value, the x value basically, is 1 plus 3 over 200 times k minus 1. Then y sub 1 is given by this formula, and if you look at that, that's this factor right here. We then assign to y sub 2k this expression's value, and that is this second factor over here. You'll notice that there is a call to a MATLAB function quad. Quad is a numerical integration function. It is going to evaluate this integral from 1 to x. You can think of this as saying the integral of, and then the integrand with it, which is this stuff right here. We're integrating with a lower limit of 1 and an upper limit of x1 sub k, which is our x value. Then, to get the value of y, we just multiply the value of y1 times the value of y2, and that is done in this statement right here, and we called that y sub 3, y3 sub k. So x1, y1, y2, y3 are all arrays, each of them having 201 values stored in them. And so what we will want to do is to plot the x values, which are in this array, versus the y values, which are in the y3 array. And that's why we have plot x1, y3 here. And then end ends this function main. If you look at this, we have something called the integrand here, and we have an at in front of it, which basically says we have a pointer to whatever the integrand is. The integrand is a function which is defined here, a MATLAB function, and it is basically just this integrand inside this integral. E to the 2 times the square root of 1 plus x cubed times sine of x divided by the square root of 1 plus x cubed. So we saw that quad is the integration operator. So quad of at a function ab just evaluates the integral from a to b of f of x dx, which is the same as the integral from a to b of f of t dt. Y1 is this first factor, y2 is this second factor, and y3 is this function that we will plot using MATLAB. If we plot that, we get this curve. This is the output of that program we just saw. Here x equals 1, and at the other end x equals 4. On the y-axis, we're going from minus 0.5, here's 0, all the way up to about 3. Now, let's remember that y of 1 equals 3. So when x equals 1, y equals 3. That was our initial condition. And now, as the value of x increases, the value of y decreases, and somewhere around right in here, I guess, it crosses the x-axis, x equals 0. And so after that, this function is negative. So this is the solution function for that initial value problem, the differential equation plus the initial condition. We can also graph this solution using a TI calculator. On the TI-86 and also the 84, FNINT is a built-in numerical integration command. We can use that for evaluating integrals such as the one that we see right here. So here's what we'll do. Similar to what we did in the MATLAB program. We'll let this factor be y1. we'll let this factor over here be y2. You can read this code in your leisure to see that it does what I just said. Then, to get the y value, we'll multiply y1 times y2, and we'll store the value in y3. Then all we have to do is use the graph command to graph y3. Now, to do this on your calculator, you'll have to use the graph command and type in these three formulas for y sub 1, y sub 2, and y sub 3. And then from the menu, you can graph y sub 3 by selecting this equation and graphing it, which probably means you'll have to unselect these first two equations. When you unselect, this equal sign, which is shaded to start off with, will become unshaded. So you want this one unshaded, this one unshaded, this one shaded before you use your graph the equations command. By the way, this you'll find out is very, very slow. I recommend you eat dinner while it's executing. Let's remember that we still need to prove that the integrating factor mu of x times the derivative of y with respect to x plus p of x times y equals the derivative with respect to x of mu of x times y of x. We got that, let's remember, by starting with the differential equation, the derivative of y with respect to x plus p of xy equals q of x. We multiplied both sides of this equation by mu of x to get this equation. And then when we looked at the left-hand side of this equivalent differential equation, we claimed that this left-hand side, mu of x times this other stuff, could be rewritten as the derivative with respect to x of the product of the integrating factor times y of x. So now it's time to prove this. To justify this method of using integrating factors, we have to show that the derivative with respect to x of the integrating factor mu of x times y of x equals mu of x times the derivative of y with respect to x plus p of x times y. Remember that this stuff right here was the left-hand side of the differential equation that we were studying. So let's see what we can do. The derivative with respect to x of this stuff, y times mu of x, by the product rule, is the derivative of y with respect to x times mu of x plus y times mu prime of x. Okay, but let's remember that mu of x is e to the integral of p of x dx. So mu prime of x up here is equal to the derivative with respect to x of e to the integral of p of x dx. Now, let's remember that the derivative with respect to x of e to the u equals e to the u times the derivative of u with respect to x. This was one consequence of the chain rule. So right here, we have e to the u, where the u is the integral of p of x dx. So according to this formula, that's going to be e to the u, e to this integral, times the derivative with respect to x of u. Now, if we look at this factor, we're taking the derivative of the antiderivative of p of x, and that is just p of x. So what we then get is that this stuff equals what? Well, this factor is mu, and this derivative we saw was p of x. So we finally get that mu prime of x is equal to mu of x times p of x. So now that we have that, we can plug that back in up here. So then we have the derivative with respect to x of y times mu of x is the derivative of y with respect to x times mu of x plus mu of x times p of x. This second term we just got up here. And notice that we now have two terms, each which has a factor of mu of x. So factoring that out, we can write this expression as mu of x times the quantity derivative of y with respect to x plus p of x times y. So we have now proven that this formula is correct, and that was the only missing link in our discussion of integrating factors for first-order linear differential equations. So let's summarize the steps in solving a first-order linear ordinary differential equation. First, we start with the differential equation, derivative of y with respect to x plus p of x times y equals q of x. We evaluate the integrating factor, mu of x, which is defined to be e to the integral of p of x dx, the p of x that appears up here multiplied by y. Then we multiply both sides of this equation by mu of x, and we get this equation. Then we notice that this left-hand side is just the derivative with respect to x of mu of x times y, and that equals the right-hand side, which is this stuff. So now we want to find out what y is, and so we're going to integrate both sides of this equation in step 5 to get the integral of the derivative with respect to x, mu of x times y of x dx, equals the integral of mu of x q of x dx. Or if we can't evaluate this type of integral using techniques of integration, we can use definite integrals instead. Change these functions. You're not really changing the functions, but we're changing the name of one variable. Change x to t. And so we have the derivative with respect to t of u of t times y of t dt equals, on the other side, the integral of mu of t q of t dt. And in these definite integrals, let t run from a to x on both sides. So we're hitting both sides of this equation with the same definite integration. Then this side is going to simplify in either of these two cases quite a bit. Up here, the simplification would be the integral of this derivative of this stuff just turns out to be mu of x times y of x. When you evaluate this definite integral over here, the definite integral of the derivative with respect to t of this stuff here, what you're going to get is, putting x in here first, mu of x times y of x, minus, putting a in there, mu of a times y of a. So on this side, we're just going to get mu of x y of x minus u of a y of a equals this integral. And then, if we can't evaluate this definite integral, we can use software, at least, to graph that sort of thing. So doing a little bit of algebra in either of these two cases, we can solve for y of x, and then from there, do whatever we want, graph it perhaps. I hope you enjoyed this lesson, and I hope that you continue watching more of these. Have a good day.